Hi everyone, welcome to today's session. We'll be talking about those response meta-analysis during this session. And those response meta-analysis is one of the additional topics that we consider that we might want to teach. This is more like a very preliminary introduction to it. We will not, we'll show you how to do it. If you're comfortable with R, you'll be able to implement the code and rerun it yourself. But we will not be teaching it in great detail. So see this as more like to whet your appetite so that you can go out and learn it some more if you want to do so. So some of the limitations of traditional meta-analysis are critical to bear in mind because they kind of help us to understand what we are able to do and what we are not able to do with the traditional meta-analysis that we would often do and which is the one that we have taught in the rest of this course, right? So the first is that the traditional meta-analysis assumes that the relationship is linear, right? So what does that mean? Essentially, what that means is that when we describe relationship between exposure and outcome relationship, we would say that for every 1 unit increase in the exposure, right, the outcome increases by maybe 1.5 units, depending on what the relative risk is. But outcome increases by the magnitude of the relative risk in fold, right? Or if this is a mean difference, we'll say that there's a difference of, but the point here is that across the entire length of the exposure, so even when you compare and say the exposure is hemoglobin, if you compare hemoglobin of 8 going to 9, or you compare 9 going to 10, or you compare 10 going to 11, right? As long as the difference is by 1 point, the effect on the outcome, say if the outcome is mortality, is the same relative risk. Now, in real life, however, a person going from a hemoglobin up from 7 to 8 is different from a person going from a hemoglobin from 10 to 11, right? Because 7 to 8 is severe anemia, while 10 to 11 is mild to no anemia, mild anemia to no anemia. And when a person has mild anemia, there might not even be any important outcomes, right? That you'll be able to measure in the person's life, depending on what outcomes you're interested in. Just using that to tell you that although we talk about linear relationships a lot, and we talk about linearity of relationships a lot, and that's the assumption that a lot of the regression that we teach initially is based on, much of real life is not linear. Much of real life is not linear. And so we use linearity to sort of approximate and give you an idea of how things are. So, if you think about this as an estimation, not necessarily the real truth. If you want to understand further, then you have to also explore nonlinearity. And one of the ways that you will do that is with the dose response meta-analysis. Okay. The other factor is that, when we do a meta-analysis, in the traditional meta-analysis, we might say highest versus lowest. And taking the anemia example again, you might say categorize people into different categories. And maybe one group had people who had hemoglobin greater than 12, and then another group had people who had hemoglobin greater than 10. But in another group of patients, the highest person's hemoglobin was 9, right? If you want to do analysis across these 3 groups, you might just say divide into 3 or 4 groups and say highest versus lowest groups, right? We've talked about that. Now, the challenge is that because we're using people across different thresholds, how do we compare the highest threshold in study A to the highest threshold in study B? So the highest threshold in study A might be 12, while the highest threshold in study B might be 11 or 10. And the highest threshold in study C is 9, right? But you want to compare that to the lowest threshold, which might also differ again. And, again, we approximate this and we use it to just give us an idea of what the real of what truth is. But we always have to understand that there is more that's under the hood, right? But in meta-analysis, when we're trying to pull highest versus lowest, right, which we often do, but we do that and we sort of close our eyes and just pull it. If we want to truly understand what highest versus lowest really means, yeah, we have to go under the hood and see what does highest mean in study A, what does highest mean in study B, what does highest mean in study C, what does lowest mean, and that way we can pull the data using the correct threshold, right? Rather than just say highest versus lowest. And we cannot do that in traditional meta-analysis. If we want to pull up by, actually pull 6, 7, 8, 9, 10 at their correct points, yeah. If you want a method that actually accounts for their correct levels, on the exposure range, then you need to do some other method, and that's where dose response meta-analysis comes into play. The third, um, the third reason, and this is basically essentially the same thing, so I guess I'll skip it, is we want to pull exposure and outcomes that are similar, right? Designed in a similar manner, that we using the same thresholds, and we'll often just throw out, sometimes we'll throw out studies that don't meet that threshold, but we will not need to do that here with a dose response meta-analysis. The dose response meta-analysis allows us to use all the data that we have. And these are just some examples of curves, right? This is a fractional curve. This is a quadratic curve, right? If you look at the graph on the left side, on the left-hand side, this is a graph of alcohol consumption and mortality risk. And on the x-axis is drinks per day. When it goes from 0 to 7, you can also look at it in terms of grams per day. On the y-axis is the relative risk, and this is 1, which is the reference, and you have the line of no effect. Okay. Now, if you look at this curve, the way to interpret this is that you will see at the beginning where if a person does not drink alcohol, there's no increased risk, right? But then as they begin to drink some alcohol, a little alcohol, maybe socially, small amounts, it looks like it protects them against mortality. And, it might not be the effect of the alcohol, it might be something else, but when a person is drinking small amounts, oftentimes because they're happy, they're socializing with their friends, they're drinking occasionally once every 2 weeks when they go out, in that range, the alcohol protects them from dying, right? It lowers the risk of mortality. But as they begin to drink so much more alcohol, now they're drinking alcohol for a different reason, right? And then you begin to have people who are there's problem alcohol intake, right? So when you start getting into that range, there's an increasing risk of mortality. And this is not a linear curve, right? This is a fractional curve. And so a traditional meta-analysis will not help us describe this kind of relationship. The same thing applies for the quadratic curve on the right, where we're looking at calcium intake, per milligrams per day in relation to the iron status. Yeah, and this is the mean difference too, and 0 is a reference. So this is also a curve where the iron status begins to reduce as you increase calcium intake. But when you get to some point, where intake of calcium is 1,000 milligrams per day, you don't have a further increase, a further decrement in the iron status. Instead, it's almost flat at this point, right? So that means that the person who is taking 1,000 milligrams per day or 1,500 milligrams per day, the impact on iron status is essentially the same, right? So if you might say, oh, if a person tells you that my dose of calcium that I'm having every day is 1,000 milligrams, I want to increase it to 1,500 milligrams, but I'm not sure whether it would have an impact on my iron status, right? You might then say, oh, it doesn't matter at this point if you're already at 1,000 milligrams per day, even if you go as high as 1,500 milligrams per day, there is no further effect on the iron status. But if you're concerned about iron status, maybe you need to decrease all the way, to 250 or something milligrams per day of calcium intake. And that's just to tell you how to interpret this graph and to tell you that there's a lot of information that is conveyed by graphs like this, by dose response meta-analysis that the traditional meta-analysis will not show. Let's take some more examples, to help you further understand why this is important to do. So if you look on the right side, yeah, on the right side here, this are a series of curves that are looking at alcohol intake from that same study, that are looking at alcohol intake and risk of cancer across different sites. Okay, across different sites. Now, when you look at, and this is looking at from 0 to 100 grams per day. Okay, what you quickly see, what you quickly see is that the shapes of the relationship are all over the map. There's so many different kinds of shapes. You go from lungs, where there's hardly no impact of alcohol intake on lung cancer, to something like oral cavity and pharynx, where even as low as 25 grams per day of alcohol already doubles the risk of cancer in the oropharynx, right? So, and then the shape as well is different. The shape as well is different. And so this tells you that there's a lot of information. Again, to just reiterate my point, there's a lot of information that you can get from looking at curves like this that tells you how to how to understand the extent of the exposure, whether there are inflection points, thresholds, and you might be able to guide your decision making based on an understanding of what the exposure outcome relationship looks like in the context of a dose response. All right. So the other thing that the dose response meta-analysis allows us to do is that it allows us to include studies regardless of the specific thresholds. Regardless of the specific thresholds. This is important because oftentimes when we conduct a meta-analysis, right? If we're conducting this meta-analysis, ordinarily we're doing highest versus lowest. We'll include this 700 and this 1650. That's highest versus lowest. In study B, we will include 58 and we will include 590 because that's the highest, right? In study C, we would include 500 and we would include 1250. You can immediately see that we're including numbers across the entire spectrum because we're going from 58, we're going to 590. And imagine thinking that 58 here and 700 here mean the same thing because we're saying lowest, right? But that's not very reasonable when you really think about it. Dose response meta-analysis frees us of having to do analysis like that are too approximated, that where the assumptions are too much, right? We can include all the data that we have, all the exposure and the outcomes that we have. The other thing, and I'll talk about, maybe I should leave that and talk about that when I get to that point. The other thing that we note here with dose response, with the dose response meta-analysis, that there are two major types of dose response meta-analysis. There's the 1 stage and the 2 stage. Okay, so in the 1 stage, you can include studies that have even just one, have even just two categories, maybe exposure, exposed, non-exposed, right? But in the 2 stage, you have to include studies that have 3 or more, right? So if you're in the 2-stage meta-analysis, you would only be able to include study A, B, C because they have 3 or more levels, okay? While for 1-stage meta-analysis, you can include all these studies, okay? You can include all these studies in the 1-stage meta-analysis. And so the 1-stage meta-analysis allows us to incorporate as much data as we need to incorporate, everything. We don't have to throw any data out. Okay. So let's take an example. Assuming we are hoping to conduct a meta-analysis of media campaigns and intake of fruits and vegetables. So as you think about it like this, you have a public health program in a community and you have made radio jingles, okay? And the radio jingles are basically saying, oh, it's good to eat fruits and vegetables, eat your fruits and vegetables, 5 servings per day. And there's a nice song and it's a catchy hook and there's beats. And you expect that if people hear this radio jingle, right, then they're going to eat more fruits and vegetables. Okay. And for your meta-analysis, so people have conducted all these kinds of studies across multiple communities, and you collect all this data, and you meta-analysis, you want to see whether whether coverage of media campaigns, and coverage here means that the number of people, the proportion of the population that actually do see or do hear the media campaign. So if there's a radio jingle, how many people heard that radio jingle? If there's a TV, TV show or TV ad, how many people see that TV ad, right? So when you think about it, if it's like 80% of population A, 10% of population B, that's the coverage, right? So you want to see whether the extent of coverage affects the effectiveness of the campaign, and you're assessing effectiveness by seeing how many people actually eat more fruits and vegetables. Okay, so that's really what we're hoping to be able to do in this meta-analysis. And so you extract your data into a sheet that looks like this, an Excel sheet, same as we've seen previously. There are two things to note, okay, is that in the previous analysis, you would extract your data in wide format, all right, in wide format. But here, you would extract your data in, so in the so in traditional meta-analysis, you extract the data in wide format. But here, you would extract the data in long format. And what does long format really mean? Long format means that each category would have its own row. Okay, that's one, that is two. Okay, this is two rows. And if like this study has three exposure levels where there's 0% coverage, 50% coverage, 95% coverage. So for the same study, 1, 2, 3, that is long format. So each exposure row, each exposure category is one row. Okay. Or yeah, each exposure outcome category is one row. And so this allows you to, so you can have many rows depending on how much data that you do have in this study. This is a key point to note for those response meta-analysis that's different from in the previous in the traditional meta-analysis that we talked about. Next thing that you will then do is visualize the data, okay? Now, if you look, so you will use a scatter plot to visualize the data like this. And if you look at this plot, the question that you first ask yourself is whether, whether the relationship here is actually linear or non-linear. So the question, so you might say, oh, if I am going to fit a line here, that the line will go something like that. Okay. And someone will say, yeah, maybe not. Another person might say, oh, maybe this is the correct line. Hmm? And another person might say, oh, maybe this is the correct line. You know what I mean? So that you can have multiple different shapes. There are multiple different shapes for the curve, right? Depending on what's reasonable. And so the first thing you want to see is look at the data and ask yourself, what's the shape that this is likely to be? In the next step is that you will then try out each shape, okay, by trying out the analysis in different forms, okay, and then use a statistical technique to decide which analysis approach, right, which model has the greatest information, okay, which model captures the greatest information in that data. And so the way that we'll look at this in multiple ways. So the first is you do a log linear analysis where you essentially, this is in those, this is in R, and you will call the dose response meta. This is the code, and like just fill this out, follow the instructions here, and you will then obtain an estimate standard error, p-values is for the fixed effects coefficients, right? So the question then will be, how do I interpret this? Yeah. So we pulled 13 studies. You remember there were 13 studies that we extracted data from and then pulled. And these 13 studies evaluated the dose response relationship of media coverage and the intake of more than 5 servings of fruits and vegetables per day. We interpret this the same way. This is log linear analysis. Remember, this is the first one. This is just doing a log linear analysis where we just take the log. And then if the p-value is less than 0.01, so that means it's significant. So we conclude that there may be a significant log linear dose response relationship. Yeah, fine. But we don't stop there. We try other shapes. Yeah, we can also scale the log linear because, if you remember, if I go back once, you will see that the beta coefficient here is 0.0071. That's becomes very small. And if you're trying to interpret 1.007 times more likely, it's not very easy to interpret. So for convenience, sometimes we will scale. And if you scale, then you might get 1.073. And, we can talk about scaling some more in the labs, but, just wanted to introduce it here. Basically, what you do is that, instead of saying for every 1% increase, now we'll say for every 10% increase. Yeah. So, or if we scale by 100, we'll say for every 100% increase, or by every increase by 100 units, depending on how we scale. Okay. So, but here we infer that for every 10% increase in the media coverage, remember we had 2 zeros before, now we had 1 zero, and this is 1.07 times, which is more reasonable. And if we're going to convert this, if it will be easier for the reader to engage with. When there's too many zeros, then it's hard to understand whether it makes sense or not. But so getting back to what we're discussing is that the first step is that you will do you will extract the data, you would visualize it, and then you will do the log linear, which is or the linear analysis, just to see what does this look like. And then the next thing is you will now start looking at the other shapes of the relationship. And you might look at the cubic, fractional, polynomial, quadratic. So what we do here is that we use cubic splines first. And so let me explain what splines are. All right. The splines are really great for examining nonlinear relationships. Splines are basically small sections. Okay, small sections. So assume that you have a long graph, right? But you cut it into small pieces, and each piece of that graph is almost, not exactly, is almost like a straight line. It's almost like a straight line. So you can fit a regression model to each piece of the range, and this allows you to get a nice smooth curve. So you can fit a model here, you fit a model there, and then you fit a model there, and then you can put it all together and you get a curve. So it's almost like you're putting the curve together brick by brick. Okay. So if you then use cubic splines for this model, we look at that and we also get a p-value of 0.001. We say, well, maybe this relationship is a significant nonlinear cubic relationship. Okay. And then we try other things. We try quadratic. Here with quadratic, the p-value is 0.1. So we failed to reject the null hypothesis of a quadratic relationship between media coverage and an intake of fruits and vegetables. But the final step to help us select a shape that we then move forward with is to use what is called the AIC. The AIC is the Akaike information criterion. And there are other approaches that we can use, but this is one that is it's really easy to implement. And you just use the AIC to compare the three models. This is or all the models that you have, depending on how many, linear, spline, quadratic, and whichever model has the smallest AIC is the model that's the best model. Okay, whichever model has the smallest AIC is the best. In this case, our linear model had the smallest AIC, and as a result, that is the best model in our case. And so what we then decide is we can then take the linear model and plot it. So if somebody asks you what's the true relationship of the coverage of a media campaign and the risk of intake of fruits and vegetables, then you will say that it's a linear relationship. This is what this looks like. And then so we plot this, okay? All right, let's take another example. So in this other example, you're interested in understanding whether the coverage of media campaigns is related to the mean intake. Remember, the last one was the proportion of those who were consuming more than 5 fruits and vegetable servings per day. Here you're saying just the mean intake in servings of fruits and vegetables per day. So we do the same thing, long format. The reference level here is 0 because we're looking at mean difference. The last one, the reference level was 1 because we're looking at relative risk, but here is 0. And we will, fill the table, extract in the same way. Again, remember this one has 1, 2, 3 because it has more than 2 exposure category levels. Okay. And then we would visualize the data. Now, if you take a look at this curve, at this scatter plot, okay, how would you draw the curve, right? You might say, oh, maybe this looks like that, right? Or someone might say, well, maybe that's maybe this looks something kind of like this. Whatever. So you might have different ideas of how you would visualize the raw data, and then the next thing will then be to run the analysis in multiple different ways. So the first step is do the log linear analysis, just like we did in the last one, and you get a p-value of 0.001. Oh, so maybe this is significant, and you try the other shapes. You do a quadratic, you get a p-value of 0.0001. That's okay, significant as well. And then you also try the spline, and when you compare them here as well, you get a linear, you get that the linear model is the best model. This doesn't happen all the time. Sometimes it's the spline, sometimes the quadratic. It just so happens that the way that this relationship is, it's just the linear that's significant. And if you plot this in R, you'll get a plot that looks like that, right? Yeah. So essentially, this is the approach to understanding the range of exposure and outcome relationship. Understanding the way that the range of the exposure might impact the outcome, across different ranges in a way that we are not necessarily summarizing and using maybe a dichotomous variable, or assuming that the exposure outcome relationship is linear, unlike what we typically do in traditional meta-analysis. So the key takeaway is that, first of all, the assumption that the relationship is linear is not always true, right? It's not always true. And there are ways for us to explore that, but there's also other advantages to using conducting a dose response meta-analysis. Beyond assessing whether the relationship is linear, it also allows us to use as much of the data that we have from the studies as possible. And we can then plot that, and have this fancy plots that we can include in our meta-analysis as well. Thank you very much.